Okay, ladies and gentlemen, so welcome to this week's Monsoon seminar. And our speaker this week is Clara Bolton from Serege, if that's the right way of saying it, in southern France. Clara did her PhD at the University of Southampton in the UK, and then she went on to be a postdoc in Spain. She's a well-known paleoceanographer, and she's here to talk to us about the Bay of Bengal and some of the work she's been doing there. As usual, what I'd ask you to do is to mute yourselves and cover your and turn off your video. If you have questions, please put them in the chat, and I'll call on you at the end to ask your question in person. So, without further ado, thank you, Clara. Please take it away.
Thanks, Peter. So, good morning, everyone, and thanks for having me at this Monsoon seminar. I'm really happy to be here and to be able to talk to you all, and to have the opportunity to present my research from IODP Expedition 353 to you. So today I'm going to talk about paleoproductivity in the Bay of Bengal and how it relates to past South Asian monsoon variations. But I'm going to be jumping a bit between different regions and also different time intervals. So hopefully my talk won't be too difficult to follow. So the work that I'm going to be showing includes many contributions from my IODP Expedition 353 colleagues. So that cruise was in 2014, December 2014. So it doesn't feel very long ago to me, but it was actually 8 years ago now. There's also a couple of PhD and master's students who contributed to the work that I'm going to be showing. So I'll acknowledge all these people throughout and at the end of my talk. It's in no means a solo effort. I received funding for this work from both IODP France and also from the French National Research Agency to carry out this research. So just a quick introduction. So the area affected by the Asian monsoon spans a massive area from the Arabian Sea in the west to the Japan Sea in the east, and as far south as northern Australia. And so understanding the Asian and the Australian monsoons over space and time is really important, obviously for societal reasons, to improve our ability to predict floods, for example, and droughts under evolving climate boundary conditions. And marine sediment cores provide some of the most continuous and long archives in which we can reconstruct monsoon variability in the past to understand the interactions with background climate. So this map on the left here shows some of the recent and more legacy deep sea drilling program, ocean drilling program, and integrated ocean drilling program and international ocean discovery program sites that have helped us understand monsoon evolution from a marine perspective. So by that, I mean, so looking at things like the impact of changes in wind-driven mixing on surface processes or circulation related to the monsoon on seasonal timescales, and also looking at things like sediment flux into the ocean from the land. So whilst precipitation and wind and surface current changes related to the monsoon are quite well understood in the modern ocean on seasonal timescales, the response of marine productivity is not so well constrained on seasonal timescales. In part, that's because it's very spatially heterogeneous and also temporally. As you can see from this satellite picture on the right of chlorophyll concentration in the surface ocean, during the monsoon season, the cloud cover means that we can't get good satellite data of chlorophyll concentration. So the response of primary productivity and export productivity to the monsoon is less well understood. So in this presentation, I'm first going to talk about some late Pleistocene records from a site from IODP Expedition 353 in the northwest Bay of Bengal. And then in the second part, I'm going to move back in time to the late Miocene and to another site in the southern Bay of Bengal, IODP Site U1443. So this slide shows modern oceanographic conditions in the Bay of Bengal during the Northern Hemisphere winter on the top row, and during at the end of the summer monsoon season in September on the bottom row. So oceanographic conditions in the Bay of Bengal are dominated by the seasonally reversing winds that are characteristic of the Indian monsoon, and by the effects of strong summer precipitation, which mainly enters the Bay of Bengal in the northern part. So during Northern Hemisphere winter, northeast winds drive surface currents southeastwards, whereas during boreal summer, strong southwesterly winds drive currents northeastwards across the Bay of Bengal. Precipitation over the subcontinent and over the ocean, as well as runoff from the major river systems, are also at a maximum during the late summer. And this leads to a strong north-south salinity gradient in the Bay of Bengal, which you can see in these figures of salinity at 5 meters depth here. So in September, we see there's a very strong northeast-southwest salinity gradient. And this freshwater input also leads to very strong salinity stratification in the northern part of the Bay of Bengal, which shoals the mixed layer. So here you can see the mixed layer depth in late summer is much reduced in the eastern part of the Bay of Bengal. And it also prevents the mixing of nutrients up into the photic zone, which has an impact on phytoplankton productivity. So in the southern Bay of Bengal, we actually see a deepening of the mixed layer during the summer monsoon as a result of wind-driven mixing, increasing the depth of the mixed layer. And that leads to the opposite effect, the injection of nutrients into the mixed layer. So in terms of primary productivity, on the western side of the Bay of Bengal, so sorry, these graphs on the right-hand side show the chlorophyll concentration in January and in September. So we can see that there's an increase, I guess, over the whole Bay of Bengal. There's a slight increase in primary productivity, which is restricted to this western margin and also this kind of southwest area around Sri Lanka. But the net effect of winds versus stratification on primary productivity is quite heterogeneous and very much depends on the interplay between winds and stratification at a given time and in a given year as well, I guess. So the two sites where I'm going to be presenting data from are sites U1446 and sites U1443, which are shown by the stars on these maps. So just a little bit more background about regional productivity variations in the Bay of Bengal. So as I just mentioned, primary productivity dynamics in this region are pretty complex and heterogeneous, and they reflect the interplay between winds and stratification. River input, although it probably supplies silicon and phosphorus to the Bay of Bengal, it isn't thought to be a significant source of nitrate. And so the phytoplankton in the Bay of Bengal are thought to be mainly limited by nitrate availability. So these maps here on the left show the different regions in the Northern Indian Ocean and when the main phytoplankton blooms occur. So on the left-hand map, this shows the regions where you have summer phytoplankton blooms, and on the right, regions with winter phytoplankton blooms. So some regions have blooms twice a year, some regions just once, and obviously the relative importance of these blooms is different in different areas. So in general, chlorophyll A, based on satellite data, is generally lower in the Bay of Bengal than in the Arabian Sea. But on the other hand, organic carbon fluxes from sediment trap studies are pretty much similar in the two basins. So this is a bit of a conundrum that people aren't really sure why the Bay of Bengal is thought of as being relatively oligotrophic, but actually the organic carbon fluxes are quite high. So Longhurst defined these biogeographic provinces in the ocean based on the primary productivity dynamics, and that's what we can see here on the right. So site U1446 falls in this East India coastal province, which has a very strong primary productivity peak during the end of the summer monsoon, so from about July to October, with quite limited but significant changes in mixed layer depth associated with that. And site U1443, which is a more kind of open ocean, wind-dominated site, has this very big peak in productivity associated with summer monsoon winds in July, August, September, and then a smaller peak during the winter monsoon, the secondary productivity peak. So also during the winter monsoon, intense winds are also thought to perhaps trigger secondary phytoplankton blooms in the northwest Bay of Bengal as well. So first, I'm going to talk about IODP Site U1446 and some Pleistocene records from here. So this site is located in the Mahanadi Basin, about 75 kilometers offshore India, so very close to the mouth of the Mahanadi River. Sedimentation rates at this site are really high, so reaching up to like more than 70 centimeters per kiloyear in the Holocene, for example. And sediments here are dominated by the lithogenic fraction. So this figure is just taken from the site report, and it shows that probably like more than 90% of the sediment is clay. And there's a very diluted biogenic fraction, which is also present. And this biogenic fraction contains carbonate and siliceous remains of marine plankton, as well as freshwater and terrestrial siliceous material microfossils, such as freshwater diatoms and phytoliths, which come in with the runoff from that river basin. So the records that I'm going to present span the last 20,000 years, so the last glacial maximum to Holocene transition. And this figure is just a compilation of data for the last glacial cycle from the Bay of Bengal from a study by Steve Phillips. And it shows that based on the oxygen isotopic composition of seawater in the Bay of Bengal, seawater oxygen isotope records, once the temperature component is taken out, they showed that delta 80 seawater was more negative in the Holocene, which suggests that salinity was lower than during the last glacial period because of a stronger monsoon and more runoff into the Bay of Bengal. So the impact of a stronger Holocene monsoon on phytoplankton productivity isn't so clear-cut. And these records in this figure from Indian National Gas Hydrate Program Site 19 show the mass accumulation rate of calcium carbonate here on the left and biogenic silica on the right. And we see that the calcium carbonate accumulation is higher in the glacial, but the biogenic silica is actually reduced. So the overall impact on phytoplankton isn't so clear. And so we looked at some new high resolution coccolith and biogenic mass accumulation rate records over these last 20,000 years, so the last transition from glacial to Holocene, to try and better understand what's hiding behind this calcium carbonate mass accumulation rate signal. So this graph here on the left shows new data from Site U1446, with at the top some high resolution records generated by Kaustul Tirumalai and colleagues of magnesium calcium based sea surface temperature in orange and seawater oxygen isotopic composition in blue. So these data are based on measurements of the surface dwelling form ruba. Clobigionoides ruba. So we can see that as sea surface temperature rises during the deglaciation into the Holocene, the seawater delta 80 becomes more negative, which is, again, like in the compilation records, suggestive of a stronger monsoon in the Holocene relative to the glacial, with more runoff and lower salinities at Site U1446. And all of these plots below show the mass accumulation rate of the different biogenic components from this same core. So starting from the bottom, this shows the total mass accumulation rate here, and the brown part is the lithogenic fraction, and the black part is the biogenic fraction. So you can see that the biogenic fraction is really diluted, especially during the Holocene when we have this massive influx of lithogenic material from river runoff. Above that, we have the mass accumulation rate of organic carbon, which again is higher in the Holocene, and the same for biogenic silica. On the other hand, calcium carbonate mass accumulation rate, which is this dark blue one, has values of 0 in the Holocene and slightly higher values during the last glacial, the deglaciation. These two brown curves up here show the isotopic composition of the carbon isotopic composition of organic carbon and the nitrogen isotopic composition of total nitrogen. And so these kind of indicate that during the Holocene, the values are more indicative of a greater contribution from terrestrial organic matter rather than marine in situ organic matter production. So this would point towards the fact that this biogenic silica and this organic carbon is probably mainly coming in with the runoff and is composed mainly of terrestrial or freshwater silica and organic carbon. So in this plot, we see the same two plots at the top, so the sea surface temperature and the delta rate seawater from site 1446 based on Ruber, and underneath we have the new coccolith records that we generated. So in grey here is the relative abundance of a particular coccolithophore species called Florisphira profunda, which is a lower photic zone dwelling coccolithophore, so it lives like under the thermocline and it's adapted to low light conditions. And so we see that this species is really abundant, making up to 80% of all of the coccoliths in the sediments, especially in the Holocene. Underneath in green is the accumulation rate of coccoliths so in terms of number of coccoliths per centimeter squared per kiloyear. And when we also estimated the mass of individual coccoliths using birefringence methods under the microscope. And so we were able to convert this into the coccolith mass accumulation rate, so the grams of coccolith carbonate per centimeter squared per kiloyear. So that's this second one below. And so the different colors in these graphs represent the contribution of different groups of coccoliths to the assemblage. So the dark green is these Noelahabdisi coccoliths, which are traditionally, in most ocean settings, the most abundant group of coccoliths, including Emiliania, Japyrocapsa, and those guys. And this light green is the Florisphira profunda contribution. So this is the lower photic zone dwelling species, which tends to be more relatively abundant when upper photic zone productivity is lower or under highly stratified conditions. So what we can see is that actually during the highly stratified conditions of the Holocene, excuse me, we have more coccoliths being exported from the upper photic, from the photic zone, and this is dominated by these lower photic zone dwelling species, Florisphira. And so again, here I've reproduced the calcium carbonate mass accumulation rate at the bottom. So clearly there isn't zero mass accumulation rate of carbonate in the Holocene as suggested by these data. And I guess the very strong dilution when these measurements were made because of the very big contribution from that lithogenic fraction means that it's below the detection limit, that actually the coccoliths are more abundant during the highly stratified Holocene than they are during the deglaciation. And so the coccolith mass accumulation rate in the deglaciation makes up about 10% of the total carbonate mass accumulation rate. And so that means that this trend of higher carbonate mass accumulation rate must be driven by foraminifera. But I haven't looked into that yet, and I don't yet have the data to support that. But I assume that this trend must be driven by the abundance of foramin. So to summarize, Profunda is a really good independent recorder of stratification at this site, and coccoliths are actually surprisingly more abundant during the highly stratified, low productivity conditions of the potentially low nutrient conditions of the Holocene relative to the last glacial. So the idea that deep photic zone coccolithophore productivity is really important in the Bay of Bengal in terms of coccolith carbonate export is supported by sediment trap data from the northern Bay of Bengal. So for example, this graph here on the right shows the calcite export by species of different coccoliths over a seasonal cycle in a sediment trap. So we can see that during the summer monsoon, the flux of Florisphira profunda, these deep photic zone species, makes up about half of the total coccolith carbonate exported. And this, it probably in some way explains why we have these high organic carbon fluxes in the Bay of Bengal with very limited surface chlorophyll detected by satellites. So just to summarize the new 1446 data. So although they're strongly diluted by this lithogenic fraction, coccoliths are actually abundant and well preserved in the Northeast Bay of Bengal sediments, with higher accumulation rates and mass accumulation rates during the stronger monsoon and higher stratification interval, which is generally inferred as a minimum productivity interval. The calcium carbonate percent data and these kind of very diluted coastal sites needs to be taken with a pinch of salt because there's plenty of carbonate in there, it's just really diluted. Floresphaera profunda dominate the assemblage throughout, especially during the Holocene. And another thing that I didn't show, but I wanted to mention because it's really interesting to me, is that during the Holocene under maximum stratification, there's actually a shift to smaller, more lightly calcified Noella habdacea or Gephyrochapsa morphospecies. So one idea is that this might be related to the very low nutrient conditions in the upper photic zone or the lower pH in the Holocene as a result of more fresh water and atmospheric CO2 conditions that might impact which morphospecies of coccoliths, whether they might make a less calcified morphotype dominate in the ocean at this time. So in the next part of my talk, I'm going to present records from Site U1443, which is in the southern Bay of Bengal on the 90 East Ridge. This is a re-drill of Ocean Drilling Programme Site 758, and it contained a continuous Pleistocene to Oligocene section of low sedimentation rate, mainly biogenic sediments. So in contrast to Site U1446, this site is really carbonate rich and is dominated by biogenic carbonate, so mainly coccoliths with a smaller contribution of foraminifera. There's also a minor clay component which increases up core, as you can see in these core images. So in the Miocene, we're almost at like 90, 100% carbonate, and as we go towards the Pleistocene, this increases to maybe 30% clay gradually over time. So in the late Pleistocene, we know that export productivity varied primarily on precessional timescales, which is shown here by 3 different independent proxies for paleoproductivity from Site 1443 over the last 500,000 years. So sorry, there's a lot of wiggles on this slide, so I'm going to go through them one by one. So at the top is the ratio of barium to iron based on XRF data. This isolates the biogenic component of barium from sedimentary barium. And so biogenic barium is made up of barite, which forms in the upper water column associated with decaying organic matter, and its abundance is linked to the amount of export productivity that occurs from the surface ocean. In pink here is the relative abundance of Floresphaera profunda, which is the lower photic zone coccolith for species that I was talking about in relation to Site U1446 before. So here you can see it's slightly less relatively abundant than at Site U1446, but we have these very strong precession cycles in the relative abundance of profunda. And this is linked to stratification and upper photic zone productivity. On the bottom graph in gray here, we have the difference between the isotopic composition of 2 planktic foraminifera species that live in 2 different depths at this site. So this is also linked to stratification. So more negative values of delta 18O reflect stronger stratification. So what we see is that all 3 of these different indicators for productivity and stratification show the same dominant precessional forcing over the Pleistocene. And so because spectral analyses revealed that this was significant, we show here in gray the precession filters of all of these records, so you can highlight this variability at this time scale. On the right-hand side here is a cross-spectral analysis of Floresphaera profunda abundance with the barium over iron record. And so this shows that the 2 different proxies are coherent in the precession band and in phase with each other. And so the dominant precession control on primary productivity at Site U1443 in the Pleistocene is thought to be linked to variations in the strength of monsoon winds on these timescales, causing mixing and the injection of nutrients and therefore higher coccolithophore productivity. However, in warmer intervals in Earth's history under different boundary conditions, we don't know much about orbital variations of the monsoon. So at this same site, we also investigated primary productivity in the late Miocene, and that's what I'm going to be talking about next. So I'm just going to quickly introduce the late Miocene because I'm making a bit of a jump from glacial interglacial timescales to longer timescales for different boundary conditions. So the Miocene spans the period from about 23 to 5 million years ago. And Earth's climate was overall thought to be a few degrees warmer than today, with slightly higher atmospheric PCO2 levels. The late Miocene, from about 11 to 5 million years ago, lies between two intervals of major cooling in the deep ocean, which are associated with ice sheet growth. And so these occurred in the mid-Miocene here, and also in the Pleistocene here, when significant northern hemisphere glaciation increased. And these kind of global cooling intervals can be seen here in the benthic oxygen isotope megasplice in this graph. And so in the late Miocene, although the benthic oxygen isotope curve only shows a relatively small increase, there's significant global sea surface cooling has been identified during this time in proxy records from the surface ocean, so magnesium calcium records and alkanone SST records. And there were also many different ecological and tectonic changes that occurred in the late Miocene that make this interval interesting in terms of global climate and also how the monsoon evolved in relation to this. So, for example, the Indonesian gateway constricted, which probably had a significant effect on circulation in the Bay of Bengal. There was the final closure of the Isthmus of Panama during this time. There was also significant ecological changes in terms of C3 to C4 transition in many different regions on land. And some proxies suggest that there was an intensification of the East Asian monsoon. Another important event that occurred in the late Miocene was the late Miocene biogenic bloom, which is recognized in lots of different sites as an increase in the accumulation of biogenic sediments over this time. And the link between all of these different things is still quite vague. And yeah, so it's a really interesting time period to look at because of all these different things that happen in parallel, and the link between them is not clearly understood yet. So in terms of the monsoon in the late Miocene, I made this map to show all of the existing late Miocene monsoon records and the main trends that are interpreted from these data. So all these dots represent different sites where monsoon records have been generated during the late Miocene, and the color on the outside of the circle is whether those proxies represent the summer monsoon or the winter monsoon or both. And the color inside is whether that study suggests an intensification over the Miocene or a weakening of monsoon strength, or, for example, in orange, a monsoon system that was already at modern strength, so to speak. So you can see that quite a few of the Arabian Sea upwelling proxies suggest an intensification at this time. On the other hand, one record from the Eastern Arabian Sea suggests the opposite trend. This record from the Maldives suggests that there was already very strong seasonally reversing winds established in the late Miocene, similar to today. And in the Bay of Bengal, there's other records that suggest intensification. So the picture's not so clear cut. And most of these records are pretty low resolution, and they don't necessarily have the resolution or the continuity to also provide information on what was happening on orbital timescales in terms of monsoon variability. So because Site 1443 has a continuous Miocene section, we analyzed this late Miocene section between 9 million and 5 million years. And so as you can see on these maps of mixed layer depth here, at 9 million years before today, this site was located, I guess, a few degrees closer to the equator, but the main oceanographic province that it was in was pretty similar to today. So it was still in this kind of southern Bay of Bengal, strongly wind-dominated region. We generated a benthic foraminiferal isotope stratigraphy, which you can see over here on the right, against depth for this interval. So we had magnetostratigraphic data that spanned the upper part, and we also refined the nanofossil biostratigraphy to have kind of some anchor points to start our tuning with. We tuned this oxygen isotope stratigraphy to an eccentricity tilt target here using a minimal tuning approach. So with one tie point every like 100 to 200,000 years to try and not artificially introduce any frequency modulations. And we used these nanofossil these refined nanofossil ages as like a starting point for our tuning. And we then used high resolution XRF data, so X-ray fluorescence data, to look at barium as an export productivity proxy at orbital resolution over this time interval. So this figure has a lot of wiggles as well, so I'm going to introduce them bit by bit. So here so again, this is the interval from 9 to 5 on the new tuned age model. And this is the benthic carbon isotope record here in black at the top. So you can see the late Miocene carbon isotope shift here, which nicely matches in timing with other records with very good age control. What we see here in blue is the percentage of calcium carbonate, which we estimated based on calcium X-ray fluorescence data. And underneath in dark blue is the ratio of calcium to the sum of terrigenous elements, so aluminium plus calcium plus titanium plus iron plus rubidium. This basically shows the ratio of biogenic to terrigenous sediment over time in the core. So both of these show a gradual decrease in calcium carbonate content, which is related to a gradual increase in clay content over this time interval. But in general, calcium carbonate content is pretty high. And we also see pretty strong orbital scale variability in these records as well. So then looking at the barium proxies, which are also based on XRF. So we looked at export productivity with barium using two different indicators. So firstly, we used the ratio of barium to a terrigenous element. So basically by normalizing to a terrigenous element, we isolate the biogenic component. And that's this up here. So we get exactly the same if we use aluminium or titanium as the normalizer. And this record below is barium excess, which is based on our calibrated XRF data. So we did a calibration and we calculated absolute concentrations. And so this barium excess is based on the barium concentration minus the aluminium concentration, basically, taking into account the barium over aluminium ratio in terrigenous material. And so both of these records show if anything, they show us the barium over iron shows a slight decrease over the late Miocene in suggested export productivity, and the barium excess showed relatively stable values over time, but both of them show very strong orbital scale variability again. So we also looked at mass accumulation rates because the concentration data and the percent data is obviously strongly influenced by dilution. And so by looking at mass accumulation rate, we can see how much biogenic barium accumulated over time and how much calcium carbonate, which is perhaps a better first order indicator of productivity than the percent or concentration data. So the big steps that we see here in the mass accumulation rates are related to sedimentation rate changes in our age model. And what we see is that, in black here is the bulk sediment mass accumulation rate, in blue is the calcium carbonate component of that, and in light blue is the coarse fraction, so mainly for planktic foraminifera fraction. So you can see that most of the calcium carbonate is made up of fine fraction coccoliths, and most of the bulk sediment is made up of calcium carbonate, so most of sediment is made up of coccoliths, basically. And what we see is this kind of step change at about 8.7 million years, where we have an increase in the accumulation of calcium carbonate, which is, you can see there's a slight increase in the coarse fraction, but it's mainly driven by an increase in coccolith export. So this could be related either to increased production or to an improvement of preservation at this time, or a combination of both of these factors. So all of these proxy records suggested relatively limited long-term trends in export productivity of the late Miocene. They certainly didn't suggest an intensification, as has been suggested by other proxies of these South Asian monsoon winds. And they all showed really strong orbital scale variability. So we looked in more detail at that orbital scale variability to try and understand whether the same drivers of monsoon winds were at play in the late Miocene as in the Pleistocene or not. So we did spectral analysis on all of these records, and we found that they were dominated by precession. And so that's what I'm going to talk about in a bit more detail in the next slide. So here in this graph in blue is the two barium proxies that I showed in the previous graph, but this time with the long-term trends and removed. So just to isolate the orbital scale variability. And so what we can see here is that when we, well, you can't see it here, but spectral analyses reveal that the dominant periodicity in these records is precession, so 19 to 23,000 years. And what we see is that this is also modulated by eccentricity, suggesting a strong control of insolation on primary productivity in this region. So these gray filters above each record show the precession component isolated, and this is the record, the raw record, but with the long-term trend removed. On the bottom here is the summer intertropical insolation gradient, which is the gradient between the interhemispheric insolation gradient in summer, which is thought to be linked to the strength of monsoon winds on orbital timescales. And we found that we had similar frequencies and similar modulation of these precession scale changes in our records as in this. Interestingly, we found that there wasn't a phase lag between our productivity proxies and between the precession and insolation records in the late Miocene, whereas in the late Pleistocene, there's a very strong phase lag between the precession-dominated proxy variations and the insolation driver. So that would suggest that perhaps in the late Miocene, internal climate processes like ice volume and high latitude processes played a more minor role than they did in the late Pleistocene, where we have these phase lags of between 5,000 and 9,000 years relative to precession. So where here there was kind of a more direct forcing of perhaps this summer intertropical insolation gradient on the strength of monsoon winds in this region, which had a direct impact on mixed layer depth and export productivity. So just to summarize these records from Site 1443. So on long time scales, our records suggest relatively stable export productivity for about 9 to 5 million years. If anything, a slight decrease in the amount of biogenic barium exported from the surface ocean, and which isn't really in agreement with records that suggest an intensification of the South Asian monsoon in the southern Bay of Bengal. On the other hand, it is in agreement with the Maldives records, for example, that show the onset of drift deposition much earlier, around 13 million years, and suggest that the South Asian monsoon winds were already like at their modern strength by the late Miocene. So quite a few recent studies have pointed towards the idea that perhaps there's a decoupling between the intensity of Arabian Sea upwelling and the long-term Asian monsoon wind intensity because of, for example, the interplay between different tectonic and paleogeographic factors that affect the Arabian Sea and the Somali jet that don't necessarily affect the wind in the southern Bay of Bengal and near the Maldives. And so our data support the idea that strong South Asian monsoon winds were already in place in the late Miocene. Another interesting observation from our data is that this important increase in mass accumulation rate of sediment, around about 8.7 million years, is mainly driven by biogenic carbonates, so coccoliths. And so it would suggest that there's an increase in productivity, or at least the preservation of carbonate at this time. And it doesn't really support the idea that there was an increase in sediment delivery to the Bengal and Nicobar fan system at this time on the 90 ridge at least, which has been previously suggested based on lower resolution mass accumulation rates, where they didn't look at what was contained in that bulk signal. And so at fan sites, there is an increase around 10 to 8 million years in sediment delivery, but this seems to be independent of the increase in biogenic accumulation that's occurring at a few of the sites on the 90 East Ridge, which are relatively isolated from these direct sediment inputs and only really receive very fine clays from these nepheloid layers. So on orbital timescales, we find that there's a dominant precession variability in our export productivity records in the late Miocene, which is consistent with what we see in the Pleistocene, but perhaps with less interference of glacial interglacial timescale and ice sheet dynamic processes, and perhaps a more direct installation control on South Asian monsoon strengths at this time. So thanks very much for listening. I've reached the end of my talk, and all of these people that I've listed here contributed to this work, including colleagues from Expedition 353, and also students who have worked with me in the last few years who I've underlined here, and yeah, other collaborators who I'm very lucky to be able to work with. So thank you very much.
Thank you very much, Clara. Oh, we have a question. Rohan, do you want to ask your question? You can unmute yourself, or I'll read it if you don't want to do that.
Hello. Hello. Hello, am I audible? Hello.
You can see his question on the chat too, Clara.
No, I can't, because I can't see the chat when I'm screen sharing.
Okay, well, maybe I'll just read it. So he says, one of your slides, you have shown that during intensified monsoon time, carbonates are also shown to increase. So my question is, how come carbonate precipitation increased in the intensified monsoon, whereas siliciclastic input would have enhanced multiple times?
I'm guessing they're referring to this data.
Yeah.
So yeah, what we see is that the production of carbonate by coccoliths is enhanced during the stratified times, but that's mainly that calcite production is mainly dominated by these lower photic zone species who are kind of favored under stratified conditions and therefore contribute a lot to the calcite and probably the organic carbon exports. I don't really know what the marine diatoms were doing at this time. That would be really interesting to look into. What we do know is that the biogenic silica in this interval is probably like a false positive because it contains so many phytoliths and freshwater diatoms that we saw in these sediments that you can't say that it's really marine productivity. And so it will be interesting to know what the marine diatoms are doing here. And I didn't understand the last part of the question about the siliciclastic.
I guess he's assuming that the boost in carbonate production shouldn't be accompanied with increased siliciclastic input. But that seems to
it's independent, I guess.
Yeah,
it's
right.
Independent because because we have this very strong runoff in the Holocene, we have this massive amount of sediment coming in, but it's mainly the upper water column stratification, I guess, which creates conditions that are favorable for this particular deep dwelling coccolithophore species.
Right.
So although the biogenic part is very, very diluted, it's still bigger than it was in the Holocene in absolute terms, in the glacial in absolute terms.
I suspect this is a slightly stupid comment, but you were suggesting that maybe the monsoon, at least at 1443, is that right? The second site, or is that 46?
Yeah.
I forget.
This is 46, 43 is
46, right.
southern.
But it might have got stronger earlier, like at the same time they saw in the Maldives. But
Right.
Doesn't the record go back that far, or is it just you haven't got looking at?
So we have so Julia Lubers and Anne and Wolfgang worked on the earlier the Miocene part that immediately comes before the part that I showed you. And they do see, based on their XRF data, that around about 11 million, they have this suggested increase in productivity based on their XRF data. So yeah, so that provides support for the idea that this kind of onset of modern like monsoon
so that's encouraging,
maybe happen there. Yeah, so that's coherent. Yeah.
So Paul Wilson has a question. Paul, do you want to just fire away there?
Morning. Nice talk, Clara. I guess my question is kind of motivated by the fact that we had this very nice presentation from Anta a couple of weeks ago, and in fact she was in Southampton on Monday, so I guess that's why it's sort of to the fore of my mind. And you referenced one of her main findings in your discussion, that is the sort of decoupling, or the potential to decouple the sort of hydroclimate, in terms of rainfall and wind signals in these various monsoon records. I guess my question is just, to what extent do you think that, obviously she can do that in a model, but when we're sort of working using cores, we're sort of, in a way, you're kind of stuck with, well, where is the core located? And so I wonder to what extent you think that the strength of the wind versus freshwater signal, the message that our data are telling us is sort of, strongly influenced by where we happen to be producing our record for sometimes rather pragmatic reasons. Thinking, for example, of the Maldives record is a long way south of the Northern Arabian Sea sites and so on. So maybe you can just kind of talk about that a bit.
Well, I guess what I was trying to highlight was that the fact that Arabian Sea upwelling does seem to strengthen in the late Miocene isn't incompatible with the idea that there were already strong seasonally reversing winds present in the equatorial region and in the southern Bay of Bengal, because the strength of that upwelling is so strongly influenced by what's happening in the surrounding mountain ranges and on the Arabian Peninsula, and that really affects the direction of that Somali jet, which wouldn't necessarily impact the seasonally reversing winds near the equator.
Okay.
Yeah, and so I guess what I was trying to say is that the Arabian Sea records that suggest an intensification of upwelling don't need to be called into question. They're completely still valid. It doesn't, it's just they're telling us two different things that aren't necessarily both just the strength of the monsoon winds.
Yeah, okay.
And as for precipitation, it's really difficult to try and understand what the hydroclimate side of things were doing, at least from the southern Bay of Bengal, because I guess it's the northern Bay of Bengal cores don't extend into the Miocene. So some of the Andaman Sea cores do extend into the Miocene, and Anne and Wolfgang and their group have done work on the oxygen isotopic composition of seawater in the very latest Miocene and early Pliocene, which suggests important changes in runoff. But in the southern Bay of Bengal, I guess the only way we have to look at runoff is by looking at the terrigenous component.
Yeah.
And that just shows a really gradual long-term increase in clay content since the Miocene into the Pleistocene. But how much, whether that's driven also by the aridification on the continent, and so more material getting put into the ocean, or whether that's really related to weathering and monsoon strength, is still an open question.
Yeah. Okay, thanks a lot.
Yes, I have to say I've wrestled with this increasing clay section and what it all means, especially as I'm predisposed not to think of it as indicating greater runoff. But of course, I could be wrong. But there are maybe other reasons for that as well. Anyway, that wasn't really the theme of your talk here. So, Sergio, did you want to ask a question? Yeah, sure.
Good morning. Thank you, Clara, for your nice presentation. I have just a
Hi.
question about your record. Have you noted any effect of this solution through time, in particular in Miocene? I mean, how is it preserved, your record, depending on intrastratal dissolution and any diagenetic effect?
Okay, so the planktic foraminifera are generally pretty well preserved in this site down to about 10 million years, and below 10 million years, overgrowth of carbonate becomes the problem as it gets more and more carbonate rich, I guess. So in the late Miocene, there's still enough of a clay component that the foraminifera preservation is good. And so we managed to do isotopes and trace elements on the planktic forams in this late Miocene interval. The coccoliths, there is a change in preservation. Hang on, I'm just gonna got a slide somewhere. So with this change in bulk sediment accumulation rate, we do see okay, so here, where we have this increase in calcium carbonate accumulation rate around about 8.7, we also see an improvement in preservation. So we see this in the fragmentation rate of foraminifera. And so I think that this increase in biogenic sediment accumulation is in part driven by improved preservation. But on the other hand, because it's mainly composed of coccoliths and not foraminifera, I think that there's definitely a productivity component in there as well. So we did look at to try and understand what was driving this transition in mass accumulation rate. We did look at the fragmentation rate of the forams, which was higher before 8.7. But in general, the coccoliths in this late Miocene interval are pretty well preserved.
Thank you, Clara. Thank you very much.
So, does anyone else have a question? If not, I'm going to ask you if you will join me in thanking Clara for her interesting presentation. And I would encourage you to come back next week. Next week is the last Monsoon seminar of 2022. It's going to be by Andre Barr, and he's going to talk to us about precipitation in the South American monsoon. It'll be on the other schedule. So if you're in Europe, it'll be towards the end of your afternoon. And if you're in East Asia, you will have to have a strong cup of coffee after your dinner. But in the meantime, yeah, please come back if you can. If not, remember, you can always look at it later on YouTube or through Zoom. But thank you very much for coming along. Clara, thank you for your time.
Thanks for having me.
Stay safe and healthy. Okay, guys. Thank you.
Bye.
Bye-bye for now.